Hi, welcome for the video going over the Chapter 1, Section 1 solutions, starting in this video with question 1. In question 1, you're asked to balance the following reactions, and they kind of wrote them in word statements, but they gave you all these formulas within it. So I've just written the skeleton equation so far. And on 1A, when you look at it, you realize that it's already balanced. 1B, fairly simple task to balance it because it's simply the O2 out of balance. So a 2 here and a 2 here will balance things. Letter C, you've got sulfuric acid and sodium hydroxide, a common neutralization reaction, which we'll do a lot of. And without setting up a atom inventory, you can pretty quickly see the 2 here is a metal that's out of balance. So if I put a 2 here, I have 2 NaOH. The H2 looks like it's balanced, but in reality it's not because I really have 4 hydrogen and 2 oxygen, so I need a 2 here. When you have, especially in a neutralization reaction where you have a base, the OH, I like to think of my H2O as HOH. And if you think of it that way, especially in acid-base reactions, it makes it much easier because water is really a hydrogen ion with a hydroxide ion. Moving on to D then, the N2H2. If you balance the N first, you'd have a 2 here, and then you would see you'd need a 3 here, and that one also balances fairly easily. E, they didn't tell you that it was O2. It says methane, the combustion of methane to produce CO2 and H2O. They will expect you to know combustion reactions, especially for hydrocarbon like methane. So to balance this one, you look at the carbon first, and that balances. Look at the hydrogen next and see you need a 2 here. And then if I look at my total oxygen, I see it will take a 2 here to finish balancing that. Number 2, they give you the skeleton equations and ask you to once again balance them. And again, these all balance fairly easily with inspection, so I'm not going to draw the atom inventory, but I'll just talk my way through it. On the first one, K plus H2O gives you KOH plus H2. Again, if I think of H2O as really being HOH, I see I have 1 OH but 2 hydrogens. So I know I'm going to need 2 OHs on this side for a total of 4 hydrogen, 2 oxygen. So now if I put the 2 here, that also gives me 4 hydrogen and 2 oxygen on the product side. And a 2 here finishes the balancing. With letter B, C2H5OH plus O2. Again, with combustion equations of a hydrocarbon, or in this case it's an alcohol, but CH and O, it's easiest to balance the carbon and then the hydrogen and finally the oxygen. So if I put a 2 here to balance the carbon, that leaves me with a total of 6 hydrogen on the left, so I'm going to need a 3 here to balance that. And now when I look, it looks initially like it's going to be trouble because I've got 4, 6, 7 oxygen. But remember, I have this one lone oxygen there, so that actually works out well that I just need a 3 here to balance it. So 1, 3, 2, 3 will balance that one. C is a pretty simple replacement reaction. The halogens trade places, so a 2 here and a 2 here will balance it. D, this is a redox equation going on. It looks kind of funny that CrO3 would become Cr2O3, but we'll learn about those a little bit later in Chapter 9. So if I put a 2 in front of the CrO3, that leaves me with 6 oxygen, and I can't get to 6 oxygen on the right side. Not exactly. So if I put a 2 in front of the O2, that gets me to 7, but that leaves me with an odd number. So I'm going to go ahead and put a 2 here instead, and then bump this up to 4 and see where I'm at. So I've got 4 chromium on each side, and now I've got 12 oxygen, 6 oxygen here, so a 3 here would give me 12 on each side. Excuse me. And then the last one, Fe2O3, if I put the 2 in front of the Fe, that means I need a 3 in front of the CO, which leaves me with a 3 here. So again, pretty easy set of equations to balance by inspection. So question number 3 wants you to balance 5 more equations using inspection. 3a is just another hydrocarbon burning. So if I balance the carbons with a 4 here, balance the hydrogen with a 5 here, when I count up, I've got 13 oxygen. So again, 6.5 works mathematically, but as far as molecules, it's not a possibility. So it's convention to go ahead and double this to 2, 13, 8, and 10. The second one, if I take a look at it, my metals are non-existent. My non-metals, nitrogen, is balanced on each side. My hydrogen, you should get pretty good at recognizing when you have 3 hydrogen on one side and 2 on the other. That means you have to balance with the least common multiple of 6, so a 2 and a 3, which means then a 2 here would balance the nitrogen. And again, when I look at my oxygen, I'm going to come up with 5 oxygen, which would require a 2.5 here. So most people would go ahead and balance this to 4, 5, 4, and 6. Now, depending on who your college prof is, they may let you go ahead and balance with halves, thinking of moles, as I mentioned earlier. Letter C, this one is just nasty because you've got NO3, and then on the right side, the NO3 remains, but then there's also NO and O, and it's not NO with O2 somewhere. So oxygen being in all 3 products makes this one just nasty. So really all you can do is guess and check your way through, and the correct solution would be that you come up with 3 carbon, or 3 copper I should say, 8 nitric acid, 3 copper nitrate, 2 nitrous oxide, monoxide I guess, and 4 water. And other than just guessing and checking until you finally come up with the right combination, until we learn to balance with what's called redox, there really isn't an easier way on that. Then looking at letter D, this one I've got nitrogen, hydrogen, and oxygen. The nitrogen appears to be balanced on each side. The hydrogen is not balanced. If I take a look at it, I have 6 on the left side and only 2 on the right. So if I go ahead and put a 3 here, so then when I have the 6 hydrogen on each side, now my oxygen is 5, and you might think, well, I can just put a 2.5 in front of the H2O2, except that doesn't work because in the previous problems, oxygen was all alone. So that won't help us get out of anything. But what you could do is you could go ahead and change this to a 4, so you have an even number of 6 oxygen, and then you could put a 3 here. And what you're going to find is now you've got 10 hydrogen, so you're going to have to change this to 5, and you're going to seesaw back and forth. And again, there's not a quicker way to do this without knowing what's called the redox method. But eventually you're going to come upon 6H2O2 plus 2N2H4 plus 2N2, and this eventually is going to become 10 to get it balanced. And the O2 doesn't become part of the balancing at all. The last one, C2HSN, is actually fairly easy. If I put a 2 here to balance my nitrogens, then I see I have 4 carbon, so I can go ahead and put a 4 here. I have 14 hydrogen, so I put a 7 here. And now I do have oxygen all alone, so if I look on the right side, I have a total of 8, 15. So I need a 7.5 here. And now once again, I can go ahead and balance this by doubling each of my coefficients to 4, 15, 8, 14, and 2. So those are the quick solutions on balancing equations. Question number 4, they're talking about mixtures, and they want you to distinguish if each mixture is heterogeneous or homogeneous. And so homogeneous is where it actually dissolves the solution. There's an attraction, it dissolves, and it's evenly spread out, becoming clear. Whereas heterogeneous, it doesn't dissolve, and it'll either separate into 2 layers or it'll remain cloudy. So sand and water, definitely heterogeneous. Smoke, heterogeneous, also cloudy. Sugar and water, that's going to be homogeneous unless you put so much sugar in there you've got some precipitating on the bottom. Salt and iron fillings, also heterogeneous, definitely no dissolving. Ethanol and water, homogeneous, that will dissolve. And steel is a homogeneous alloy where they heated the metals up to liquids, and then when they cool them down, it forms a homogeneous solution, solid solution.